Hello, this is Jared Niemi with a mini lecture on the one-way ANOVA F-test. So previously we talked about a number of tests that can be used in the scenario where you have two samples, and these tests were tests of location. So typically either stated in terms of means or medians. And we can break these tests up into four different categories. We can break them up by whether the tests themselves are parametric or non-parametric, and whether the tests are used on data that are independent or paired in these two samples. And all of these tests, with the exception of the permutation test that we also talked about, make some distributional assumptions. In particular, even the non-parametric test typically assumes some kind of shape of the distribution being the same between the two samples. More importantly, the parametric test assumed having actual normality of the data. So in particular, the t-tests assume this kind of structure. So we have observations in group I, and this is observation J. They are independent and normally distributed, whose mean and variance both depend on which group they're coming from. And we might make additional assumptions, for example, in the two-sample t-test, where we assume that the variance or the standard deviation is the same amongst all the groups. And although we're making these assumptions, and they might be somewhat strong assumptions, we also pointed out that the t-tests are robust to departures from these assumptions. That is, even when these assumptions aren't exactly met, the t-test still seems to perform well as a test for the location difference between two groups. Alright, so now we're moving on to having more than two groups, and we have exactly the same assumptions that we had in the two-sample t-test. We still have groups I and observations J within that group, independent, normally distributed, whose mean depends on the group, and a common variance amongst all the groups. And what's changed now is that the number of groups before was just I and 1, 2, so there are only two groups. Now we're going to have capital I groups. Alright, and in each group we have n sub I observations. So one way of visualizing this assumption is the figures right here. Alright, so here is two different examples. There are four groups. The four groups have different colors. In each example, we actually have the same difference between the means and the groups. That is, the difference or the distance between the peaks on all these curves is exactly the same as it is here. Alright, but what's different between the two examples is the variance. So in this case, the variance is much larger than the variance is here. Alright, but this is the idea of the ANOVA assumptions, is that we have the same shape distribution for all of our groups, and what's different between the groups is where that distribution is centered. Alright, so the one-way ANOVA F-test looks at those means and says, alright, let's have a null hypothesis that says that all of the means are exactly the same. So this notation here, mu I, right, that's the mean for each group. So each group has exactly the same mean. We're going to just call that mu. And the alternative hypothesis then is just the opposite of that. And the opposite of that just says that at least some mean is different from the rest. They don't all have to be different, just at least one has to be different. Alright, so here's a graphical depiction of these hypotheses. So using exactly the same two data sets, or the two examples we had before, now we have in the top row, we have the null hypothesis, and in the bottom row, we have the alternative hypothesis. So in the null hypothesis, we have the same distribution for all of our groups. Right, in this case, we have a wider variance than we do in this example over here. Then in the alternative hypothesis, we have the same distributional shape, but it's shifted in location. That it's the mean of this distribution, where it's peaked, is shifted for each group. Now, there's nothing about the hypothesis that says that that shift has to be exactly the same like I've depicted here. Right? Again, all the alternative is saying is that at least one of the groups has a different mean. Alright, an alternative way that we could write this is we could write this in this format saying, alright, these observations right here are independent and identically distributed from the same exact distribution. Right? So that all of our data just come from a normal distribution with a common mean and a common variance. That would be the null hypothesis. And the alternative hypothesis would be exactly what we saw on the last slide. That is, that each of our observations comes from a normal distribution. They're still independent, but they come from a normal distribution whose mean depends on which group they're coming from. All right, so these are the two models, and the F-test basically says, all right, if this model is true, how unlikely are the data that we observed? And they do this through an F statistic that we're going to be calculating in a second. All right, so here's the two models. We have a full model. So this is new terminology that we're introducing. The full model is going to be the model that's sort of as broad as we get when we're comparing these two. And then the reduced model is going to make some assumptions relative to this full model. So let's just get an example. All right, so here the full model is the model that we write down in the alternative hypothesis. Right, so in this case we have the observations are independent, normally distributed, but each mean is different and depends on the group membership. In this full model, we're going to estimate each of these means separately, one for each group. Right, so we're going to take all of the observations from group 1 and we're going to estimate that mean. Then we're going to take all the observations from group 2 and estimate that mean. And we're going to estimate the mean by just taking the sample average of the observations in that group. So y bar I here is just the average of all the observations in group I. And that's the same as what's written here in the notation. Alright, in order to construct this one-way ANOVA F-test, we have to have this idea of a residual. So a residual is basically just the difference between what we did observe and what we would expect to observe. Right? So in this case, it's what we did observe, Yij, minus the average of that group. Right? We know there's going to be some variability around that average, but nonetheless, we expect that the observations we're going to see falls around that average. So the residual is just the difference between what we did observe and what we would expect to observe under the full model. Now we can calculate this, the sums of squares of these residuals. So we just take the residuals and we square them and we add them all up. So this notation right here with the two summation signs is just saying do that summation over all of the groups, right? All of the observations in all of the groups. Alright, so now we're going to do exactly the same thing we did for the full model, but on the reduced model. So the reduced model is our null hypothesis. Our null hypothesis says that all the means are the same. And in this way, this model over here is a reduced version of that model. That is, it's a simpler version. Right? This model has different means for each group. This model has one mean for all the groups. And now we're going to estimate that mean by taking the average of all of our observations. Because under this hypothesis, there's only one mean, so now we can use all of our data to estimate that mean. Alright, we're going to do the same thing here with the residuals, and under the reduced model, now we take the observations that we have and we subtract that overall mean. Because under the reduced model, we only have one mean, we have one estimate of that mean, and so that's what we use to calculate the residuals. The sums of squares are calculated exactly the same. But now I want to point out here that we give this new terminology or new notation. So this is sums of squares total, and the one for the full model is the sums of squares error. Alright? So this is basically, with the simplest model that we want to really think about, this is the total sums of squares that we could possibly have. And if we want to have a somewhat better model that allows the locations to be different, this is how much of the sums of squares end up in the error, that is, are accounted for by this sigma squared term. Alright, so sums of squares error corresponds to the full model, sums of squares total corresponds to the reduced model. Alright, so here is an ANOVA table for computing the test statistic that we need for this one-way ANOVA F-test. Alright, so we already talked about the sums of squares total and the sums of squares error. Right, we're going to see on the next slide that the sums of squares A, that is the sums of squares that are associated with the factor, this is the group membership, that the sums of squares A plus sums of squares E is equal to the sums of squares total. Alright, so that's this sums of squares line for a one-way ANOVA table. On the degrees of freedom column, what we put here is the number of groups minus 1, the number of observations minus the number of groups, and then if we add these two up, then the i's cancel and we get the number of observations minus 1. Alright, so that's the first two columns, the sum of squares column and the degrees of freedom column. Then we calculate the mean square error, or the mean squares. The mean squares are just this column right here, the sum of the squares column, divided by the degrees of freedom column. Right, so here is sums of squares a divided by I minus 1, and sums of squares error divided by n minus I. And we don't calculate this one down here because we won't need it for the test statistic calculation. This spot in the ANOVA table right here is our estimate of sigma squared. So this is the pooled estimate of the variance in this mean squared error line. I say the mean squared error line because it's under the mean squared column and it's in the error row. So this is the mean squared error line. Alright, so this is one way to remember the ANOVA table, but there's an awful lot of equations here, and so we're going to write down a simpler form. So here we have, I've told you how to calculate sum of the squares total and how to calculate sum of the squares error. So we get sum of the squares A just by taking SST minus SSE. Here again is the degrees of freedom. It's the groups minus 1, number of observations minus the number of groups, and then number of observations minus 1. Mean squared error is just S sums of squares error divided by its degrees of freedom. And the mean squared associated with factor A is just the sum of the squares associated with factor A divided by its degrees of freedom. Right, so this mean square error, this mean square line is just again this row divided by this row, or this column divided by this column. The F statistic that we're actually going to use or the test statistic I should say, that we're actually going to use to determine the p-value for this particular test is the ratio of the mean square for factor A divided by mean square error. So it's the ratio of those two. Now it turns out that that ratio, if the null hypothesis is true, has an F distribution. The F distribution has two parameters. It has the numerator degrees of freedom and denominator degrees of freedom. The numerator degrees of freedom are just the degrees of freedom in this line, I minus 1, and the denominator degrees of freedom is in this line, n minus I. Notice here that we have MSA divided by MSE. MSA is here, so the degrees of freedom associated with that is this. MSE is here, it's in the denominator, its degrees of freedom are there. Alright, so the larger the value of this F statistic indicates more support for the full model or against the null hypothesis model. Right, so the larger this F statistic, and the larger this F statistic, the smaller the p-value is going to be. Alright, this p-value is calculated right here. It's the probability that an F distribution with I minus 1 numerator degrees of freedom and n minus I denominator degrees of freedom is greater than this quantity, whatever it is. So a small p-value provides evidence against the null hypothesis. Alright, so here's an example. So here's 6 different groups. The groups are defined by their diets. So we have 6 different diets, and then we record the lifetime of a number of mice on each of these different diets. And so one of the questions we have then might be, are the means of all these 6 groups the same? Right? So they certainly don't look the same in this picture, and so the question is, are they statistically significantly different? Or said another way, could these data have happened just by chance, even if they were the same? Alright, so here on the right side is just the number of observations that we have in each group. So we have around 60 observations in each group. Alright, so here's the SAS code to do the one-way ANOVA, or at least one way to do it. The data step up here should be familiar by now. I have replaced the delimiter statement by this DSD statement, which will work just as well. Now we're going to use this proc GLM. So GLM stands for General Linear Model. We'll get back to that more in a bit. So just like before, our explanatory variable goes in the class line, And in particular, this is going to be an explanatory variable that is a factor. And we'll talk about that a bit later. The next line here, instead of having the var statement like we had before in proc t-test, now we actually have a model. And the reason for this is because we're going to be using this same proc for much more general structures. So for right now, just remember what we're going to do is on the left side of this equal sign, we're going to put our response variable. In this case, it's the lifetimes of the mice. And on the right side of the equal sign, we're going to put our explanatory variables. In this case, it's those 6 diets. Alright, so this SAS code right here will result in this output right here. And this, in fact, is the ANOVA table. So now, relative to the diagrams I showed earlier, the sum of squares and the degree of freedom columns are swapped. But not other than that, it's exactly the same table. So here's the sums of squares total. Here's the sums of squares error. This would be the sums of squares A that we were talking about before. We have the degrees of freedom. So here, this is the number of groups minus 1. So apparently there were 6 groups. This is the number of observations minus the number of groups. And this is the number of observations minus 1. So apparently there were 349 observations. To get the mean square lines, we just take the sums of squares and divide by their degrees of freedom. So this line right here is just 12,733 divided by 5. The mean squared error, right? This is our estimate for sigma squared, or our pooled variance. It's calculated by taking the sums of squares for the error line and dividing by its degrees of freedom. The F statistic is derived by taking the mean square for the model divided by the mean square for the error. And then the probability that an F distribution with 5 numerator degrees of freedom and 343 denominator degrees of freedom is greater than 57.1 is less than 0.0001. So this is a pretty small p-value. So we would say that we reject the null hypothesis that all the groups have exactly the same mean. Alright, so in summary, here's the model that describes the one-way ANOVA F-test. It looks exactly the same as the 2-sample t-test, but now we have more than 2 groups. Right? We have capital I groups. The test actually tests this hypothesis. The first hypothesis is that the mean in all these groups is exactly the same, and the alternative hypothesis is that at least one is different. And the ANOVA table that we described is a convenient way for organizing all of the relevant quantities for this test and computing the p-value. Thank you.